So now let us just try to stay afloat and keep swimming on to the next part of exercise 10, which is C, in which we are asked to show that two events are independent. Namely, that we want to show that the event that W1 is smaller than W2 is independent from the event that the smallest of them will be greater than X for any X greater than 0. So whether or not the smallest of W1 and W2 is greater than some value will not impact whether or not it will not impact which of them is greatest or smallest. That's what we can conclude from this. So how do we show this? Well, first of all, let's just observe an interesting thing that we will also use in part D, which is if I have stochastic variables, some stochastic variables x1, x2, and so on, and I want to consider their minimum. Yes? And I want to look at the event where their minimum is greater than some value. So I want to consider the event that the minimum of x1 up to xn is greater than some value, x, this event. Well, what is this event the same as? If the minimum of each of these x's is greater than x, then that means that both x1 has to be greater than x, and x2 has to be greater than x, and x3 has to be greater than x, and so on. So they all have to be greater than x. And when I say all of these have to be true, then what I mean is I intersect all of these events, yes? So this is the event for xi being greater than x. I intersect all of these events, for I going from 1 up to n. So the event that the minimum of n stochastic variables is greater than some value is just the same as the intersection of each of them being greater than that value. And we will use this again and again, not just in this course, but also in advanced probability courses. So let's also just continue on a little bit with what else we need as prerequisites to solve this. Well, we want to show that two events are independent, right? So let's just recall what it means that two events A and B are independent. Well, they're independent if and only if the probability of A intersected with B factorizes into the probability of A and the probability of B. So what we want to do now is we want to show that the probability of the intersection of the two events here factorizes into the probability that W1 is smaller than W2 and the probability that the smallest of the two is greater than X. So, well, let's just get started from somewhere. So, we will need to calculate both this thing and this thing and this thing. So we need to calculate three probabilities. The first probability that I think we can start working on is the probability that the minimum of W1 and W2 is greater than X. Because that one is actually pretty easy. So this event that we have inside here is the same event as W1 greater than X and W2 also greater than X. And recall that the interarrival times are independent, so in particular W1 and W2 are independent, which means I have the probability that W1 is greater than X multiplied by the probability that W2 is greater than X. In fact, they're not just independent, they actually both have the same distribution, which was exponentially distributed with parameter lambda. So what I have is that this thing here is the survival function in the exponential distribution with parameter lambda, and the next one is also, so multiply by e to the minus lambda x. So this gives me e to the minus 2 lambda x. So that was the first one that we took. It's the probability that the minimum of W1 and W2 is greater than x. Okay, so now let us continue on to the next calculation, well, let's just say now I want to calculate the probability that W1 is smaller than W2. Which color should I choose? I will choose some kind of pink. So the probability that W1 is smaller than W2. So we can do this a couple of different ways. Let's just do it the conditioning way for fun this time. So this is the same as the probability that W1 is smaller than W2 given W2, for example. And since given W2, and then we will take the mean value of that. So let us just try to calculate this. The mean value given W2. Then in order to take that, I will have to integrate with respect to W2. And the thing I want to integrate is the density, the marginal density of W2. And inside here, what I have is the probability that W1 is smaller than W2, given that W2 is equal to W2. And we let that go from 0 to infinity. And let's just recall that the marginal density of W2 is given as e to the minus lambda W2, with a lambda down here as well. And given that W2 is equal to little w2, well, then the probability of W1 being smaller than W2 is just the probability that W1 is smaller than the value W2. And this is equal to the integral from 0 to infinity, lambda e to the minus W2. And then I have 1 minus, what do I have? 1 minus e to the minus lambda W2 up here again. And the reason why we have that is because I'm looking at the distribution function of W1, which is exponentially distributed with parameter lambda, right? So what I've written down here is just the distribution function. So now what do we have? I have the integral from 0 to infinity of lambda e to the minus lambda W2, dW2, minus the integral from 0 to infinity of, let's see, lambda e to the minus lambda multiplied by 2 multiplied by W2, dW2. And what is this equal to? Well, this is equal, the thing over here, this is just a 1, right? Because I'm taking the density function in an exponential distribution and integrating it over the entire support. So this is just equal to 1. And what is this thing equal to? Well, we can kind of see that if I had multiplied a 2 inside here, so I will take a half out here, and then I will multiply by a 2 inside here. So I can do that. then essentially inside here, the integrand is also a density function in the exponential distribution with parameter 2 lambda. So this also integrates to 1. What the fuck is going on? Does it really just integrate to 1? Okay, yes, it does. Okay, well, sorry, I was just confusing myself. This integrates to 1. So what I have here is 1 minus a half. Well, this is so brilliantly simple that I got confused. And this is a half. So let's just evaluate again what it was we found the right-hand side to be. So in conclusion, we have that the right-hand side, so the probability that W1 is strictly smaller than W2 multiplied by the probability that their minimum is strictly greater than X is given as 1/2 multiplied by e to the minus 2 lambda x. So the thing is, now we're kind of hoping, right? We're kind of hoping that when we evaluate the probability of the intersection of the event, so the probability that W1 is smaller than W2 and the minimum of the two is greater than X, when we evaluate this, we're kind of hoping to get the same expression. And if we have the same expression, then we will be done. So let us just try and see what we get here. First of all, we notice that if we consider an event where W1 is smaller than W2, and the smallest of them has to be greater than X, then, well, we already can see that when W1 is smaller than W2, then the smallest of the two is equal to W1. If W1 is smaller than W2, right? So this thing here is just the same as saying that W1 should be greater than X. And this is kind of nice because now we've split this up into something that we can control a bit more. So let us just try to look at how this thing looks. We've already worked with the conditioning argument that we used up here, right? So we've already worked with that kind of argument. So now let's just take a good old probability calculation argument. I want to find the probability that W1 is smaller than W2 and that W1 is greater than little x. So I can attack this in a number of different ways. The way that I would choose to attack this is to say, well, I want to find the probability first and foremost that W1 is greater than X. So I integrate from X up to infinity with respect to W1. After that, I want to find the probability that W2 is strictly greater than W1. So I will integrate from W1 up to infinity over W2. And the thing that I integrate needs to be the density that controls the distribution of W1 and W2, which is the joint distribution, the joint density of W1 and W2. Okay. So let's just recall very quickly that W1 and W2 are independent, right? That means I can factorize the joint density into the product of the marginal densities. So what do I get? I get from x to infinity, and then the integral from W1 to infinity. And what else do I get? I get that the density inside here is lambda multiplied by e to the minus lambda W1 multiplied by lambda e to the minus lambda W2. dW2, dW1. Well, this is quite comfortable because now I have x to infinity out here, and then I have lambda e to the minus lambda w1. And then inside, I want to evaluate the integral where I integrate this density with respect to w2 on a certain set. Now that is not really that hard because I just take a density and integrate on w1 to infinity. So what I actually have here is just the probability that w2 is greater than little w1. Just erase this here. Put this here. Okay, great. So what's the next step? Well, the next step now is just to plug in everything that I need, because I can take the lambda outside. I have integral from x to infinity, e to the minus lambda w1, and since w2 is exponentially distributed with parameter lambda, what I have inside here is just again lambda e to the minus lambda w1 dw1, and that is equal to lambda squared, and then I want the integral of e to the minus lambda multiplied by 2 multiplied by w1 dw1. And this is quite comfortable to calculate because this is just lambda squared, and then what I have is the integral, so let's just see. Antiderivative here is minus 2 lambda e to the minus 2 lambda w1, and then I guess I have some kind of 1 over here. So is this all working out as it should? No, it isn't. And the reason why it isn't is because I have an extra lambda here. So I want to apologize for that. The survival function that I'm looking at, it does not have the extra lambda. This extra lambda is only there if we are looking at the density, right? So let me just write this up just so that we're completely clear. The probability that w2 is greater than some small value w1 is given as e to the minus lambda w1. Whereas if I was looking at the density of w2 and w1, then the lambda would be there. So because this lambda isn't here, then the squared isn't here either, and the squared isn't here either. So this looks a bit more correct. And then we have lambda multiplied by 1 over lambda, and I'm evaluating this thing from x to infinity. And what we are left with is 1/2 e to the minus 2 lambda x. Oh, that was nice, because I have just concluded that the probability of the intersection of these two events is 1/2 e to the minus 2 lambda x. I just concluded that by calculation. And that is in turn the same as the product of probability of each of the events. So now I have shown that w1 smaller than w2 is an event that is independent from the minimum of them being greater than x. So hence, let's just write this here, is equal to the product of w1 smaller than w2 multiplied by the, is equal to the probability of w1 being smaller than w2 multiplied by the probability of their minimum being greater than x. And hence, what can we conclude? Hence, these two events are independent.